Today we are going to be talking about section 3.8. This is about the related rates. We are going to have some equations in variables. We are going to have a couple of equations relating the variables, and then afterwards we are going to take derivatives of these variables with respect to the same independent variable and relate them. That's why this is called related rates. And we will talk about the word problems, as you would see, and afterwards solve a couple of word problems related to this related rates. Let's look at the example one in our book. What is the problem? Let's read. Water runs into a conical tank. So we have a conical tank and water runs into the conical tank, and the rate at a rate of 0.25 meter cube per minute. So every minute there's 0.25 meter cube water added to the tank. The tank stands point down and has a height of 3 meters, as you will see in the picture here. You have 3 meters high and a base radius of 1.5 meter. 1.5 meters up here. This is the radius of the base. How fast is the water level rising when the water is 1.8 meter deep? That's the question. Now, first thing you will do is try to understand this question. And we are talking about the rate of change of water getting into the tank and rate of the water level rising that they are asking about. Okay, so there are two rates that they are talking. But before we do that, first let's state the variables. First thing, we let V to be the volume in terms of meter cube of the water in the tank at time t, and the time is in terms of minutes, and x is the radius of the surface of the water at time t. Look at the picture. X, okay, this green part is the water that's rising, and it's going to look like a cone, right? It's going to be a cone in shape. And since it's a cone, the base of the cone has a radius x in here. As the water level rises, this x is going to increase. And also this y represents the level of the water, okay? And this y is going to also change as time goes on. So this y is depending on time, and this x depends on time, and this volume in the tank, volume of the water in the tank, depends on time. So all these variables depends on, we have three variables, as you will see. One independent variable. Independent variable is time, and volume depends on time. The level, the height of the water depends on time, and the radius of the this cone, depending on the water shape here, depends on time, increases as time passes. So y is the depth of the water in the tank at time t. Now, of course, here we assume that this volume function, volume v, x and y are differentiable functions of t. Okay, this is an assumption. The constants are the dimensions of the tank. Okay, so y is equal to 1.8 meter. It is, they're asking when, what's the rate at whenever the height is 1.8. Okay, so these are constants. 3 meter is a constant, 1.5 is a constant, they don't change, and dv dt is given to be 0.25. What is this rate of change of the volume with respect to time? Okay, so how are we going to relate all these variables? We know the volume of a cone. The volume of a cone is the base area times height over 3. Okay, so therefore, as you would come to this equation here, pi x squared x, so we are interested in writing the volume of the water, okay, of this tank, of this cubic shape of the water. So what's the volume? It is pi times x squared is the base area, and the height is y, and we are going to divide it by 3. This is just a formula coming from the cone volume. Cone volume is like that, okay? So we got this formula, and this is a relation. This shows the relationship between the volume of the water and the x and the y. So that's why actually this is called the related rates. There's a relationship between the variables. also because of that there's going to be a relationship between the rate of change of the variables. All right, and next thing is, so we have this formula, but this formula is not enough to continue. Now I remember your geometry knowledge from high school. You have this Taylor's, we have this Taylor's relationship, which is you are having this similarity of the triangles, you can also call it. We have a big triangle here and we have a small triangle here, and because of the similarity of these triangles, we have x over 1.5, I'm sorry, y over 3 meters. So we have such a relationship that comes from the geometry here. Okay, or you can write it as x over y is equal to 1.5 over 3. So let's get that. X over y is equal to 1.5 over 3. It's the same as x over 1.5 is equal to y over 3. Okay, so similarity of triangles gets us there. Okay, and see, it says similar triangles here. So from here I can find a relationship between x and y only. Okay, excluding y, v excluding v. Okay, so since we have this relationship, I can take that x value and put it in my v equation here. If I put it in, then v is related to the y variable only, which is good, because this is gonna make my job easier. So when you put y over 2 into x, you have y over 2 squared y. If you combine them, you have y squared here y, it becomes y cubed. 2 to the second power gives you 4. 4 times 3 is 12, and we have this v is equal to pi over 12 y cubed. And then what do? We are going to, so we have v in terms of y only. That's good. We take the derivative with respect to t now, because v depends on t, y depends on t. Take the derivative of v with respect to t, and then do the same on the right hand side. Take the derivative with respect to t. Okay, if you take the derivative with respect to t, this is the power chain rule. Pi over 12 sits there. Take the 3 into front, decrease the power by 1, and take the derivative of y with respect to t. Okay, and then you simplify it, you get pi over 4 y squared dy dt. Alright, so so then what do? We know what dv dt is. It is given 0.25. We put it in, and then we know why. It says find the rate of change of the height, which is dy dt, whenever y is equal to 1.8. So we know what y is equal to 1.8. We put it in, and then from here we isolate dy dt, and we got that 0.098. So what does it mean? At that time the water level is rising at about 0.098 meter per minute. Okay, that's the final answer to this. So let's summarize how we are going to approach these related rates problems. What's the strategy for that? So first of all, we are going to draw a picture, and we are going to name the variables and constants, and usually we are going to have t for time. Okay, and we are going to, of course, assume that all the variables we are considering are differentiable functions of t. Then we are going to write down the numerical information we have. We should do that in terms of symbols, and you can choose your own symbols. You don't have to use somebody else's symbol. Write down what you're asked to find. Usually you are going to be asked a rate, so write down the rate that they're asking in terms of symbols. Okay, write an equation that relates to variables. This is very important, as we did in the previous question. We related the volume with respect to x and y. So first thing you're going to do is write an equation that relates to the variables. Here you may have you may come up with 2 or more equations at first, and then you may need to combine them. Okay, depending on the questions. So don't worry that if you have getting more than one equation, because sometimes having more equation that shows the relationship between the variables is not enough. Okay, so you're going to have two or more equations, try to get them out depending on the number of variables, and then you're going to combine them to get to the an equation that you're going to use the variable in terms of one single variable at the end. Okay, so then you're going to differentiate the equation that you got with respect to t. So you want to express the rate you want in terms of the rates and variables whose values you know that are given in the question, and then you're going to evaluate, namely you're going to use the given known values to find the unknown rate that you're asked to find. Okay, so these are the steps that you have to go through. Let's solve another example. This example is about a hot air balloon that's rising up, okay, straight up from a level field, and there is a range finder that is tracking that balloon. Okay, and this range finder is 150 meters away from the liftoff point of the balloon. Okay, the balloon just is raised at this point, it's raising up, and this range finder is 150 meters away from this liftoff point. Right now it says at the moment the rangefinder's elevation angle is pi over 4. This theta is pi over 4, and the angle is increasing at a rate of 0.14 radians per minute. The question is, how fast is the balloon rising at the moment, at that moment when the elevation angle is pi over 4. So we are going to first draw a picture, which is actually drawn here. Thankfully we have that, and we are going to apply the strategies that we discussed in the previous strategy table. Okay, so draw a picture and name the variables and constants. Okay, so we have the balloon here, we have the rangefinder 150 meters away, and then the height of the balloon is y. Okay, and then this angle is theta, it's named, and we are given that the rate of change of theta with respect to time at when theta is equal to pi over 4 is 0.14 radians per minute. This is also given, and they are asking that what is dy dt when theta is equal to pi over 4. That's what they are asking you to find. Okay, so again, theta is the angle in radians the rangefinder makes with the ground, and y is the height in meters of the balloon above the ground. Okay, t represents the time in minutes. Okay, we assume that theta and y are differentiable functions of t, and alright, so we are going to write down a numerical information which is d theta dt, which this is set in the question, but we have to formulate it, and this is d theta dt is equal to that. We have to write it down when theta is equal to pi over 4, and write down what we are to find. The question wants us to find dy dt when theta is equal to pi over 4. We write it down, and then we write a relationship, write an equations that relates the variables y and theta. So we have a right angle triangle here. So we have this tangent theta is equal to y over 150 meters. So this is a good relationship between y and theta. Okay, from here we got y is equal to 150 tangent theta. Then what are we going to do? We are going to differentiate this with respect to, using the chain rule. Okay, so we are going to differentiate both sides with respect to the chain rule. Using the chain rule, how would you do? The derivative of y with respect to t is dy dt. On the right hand side, since theta depends on t, this is where the chain rule comes from, and 150, the derivative of tangent is secant squared theta, and then don't forget to take the derivative of theta with respect to t, because theta is a function of t. This is the chain rule we apply here, and then we are going to evaluate what we have in hand. We are given d theta dt, put it in, and we are given theta, which is pi over 4, put it in, and we got that dy dt is 150. Okay, and secant pi over 2 is square root of 2, which is secant pi over 2 is 1 over cosine pi over 2, pi over 4, I'm sorry, pi over 4. Cosine pi over 4 is square root of 2 over 2, and when you raise it, when you take the reciprocal, you get square root of 2 on top. So it's square root of 2 squared times 0.14, you get 42. Okay, this is at the moment in question, the balloon is rising at the rate of 42 meter per minute. So after 1 minute, the balloon is going to rise 42 meters. Okay, that's what it shows. Let's look at example 3 in our book. This is a nice example as well. One needs to know because we are going to learn new things in this question. What does this question say? There's a police cruiser, okay, and it's coming to a right-angled intersection. As you would see here in the picture, this is 0 is the right-angled intersection from the north. So a police cruiser is this, it's coming from the north to this intersection, and this police is chasing a speeding car. Okay, this is the speeding car. Speeding car has turned the corner and it's moving towards, it was coming down here, it moved towards east, and it's moving towards east now. Okay, and when the cruiser is 0.6 kilometer north of intersection and the car is 0.8 kilometer to the east, the police determined with radar that the distance between them and the car is increasing at 30 kilometer per hour. Okay, so there's a distance between the two, which we show as s, and the change in s is 30 kilometer per hour. That's what the police determined using the radar. If the cruiser is moving at 100 km per hour at the instant of measurement, what is the speed of the car that they are asking? Okay, they want to know what the speed of the car is at that moment. So first thing we do is we draw the picture. We draw the picture of the car, we draw the picture of the cruiser. Okay, the coordinate axis and right, and the directions that they travel to. Like for example, this shows that the police car is traveling towards south, and this arrow shows that the speeding car is traveling towards east. And x, we need to name some x and y's to the distances. So for example, at this moment, the police cruiser is y kilometers away from this origin, and x is this speeding car is x kilometers away from the origin. Okay, so x shows the position of the car at time t, and y shows the position of the cruiser at time t, and s is the distance between these two cars. Okay, at time t, of course. These are x, y, and s. They all depend on time t. All right, and then of course we assume that x, y, and s, they are differentiable functions of t, and we are interested in the x dt because that's what they are saying. What's the speed of the car, speeding car? Okay, that's the same as the x dt. Okay, so when x is equal to 0 kilometer, 0.8 kilometers, y is equal to 0.6 kilometers, that they're asking, and dy dt is negative 100 kilometer per hour, and the s dt 30 kilometer per hour. Now you can ask why we had written dy dt as negative 100 kilometer per hour. Okay, because in the question, let's go up here, it says the cruiser is moving at 100 km per hour at the distance at the instant of measurement. It doesn't say negative 100, but when you're talking about the velocities, you would like to put consider a positive direction for yourselves. So usually this is a positive direction, this is a positive parts of x and y are positive direction, and negative parts of x and y are the negative direction. So in this case, police is moving towards negative direction, so we put this negative in front of 100 km per hour. Alright, so And then we have this right angle triangle, which is going to give us the relationship between x, y, and s. So here is the s squared, the distance equation. S squared is equal to x squared plus y squared. We are going to use this relationship. Okay, and then what do? We are going to take this and take the derivative of all sides with respect to time, and we are going to use the chain rule again. So take the derivative of s squared, it is 2 times s ds dt, and then take the derivative of x squared with respect to time, it is 2x dx dt. Take the derivative of y squared with respect to time, it is 2y dy dt. And now what do we know? Which ones do we know? We know dy dt, we know ds dt, but we don't know dx dt. Alright? And we know x, we know y, so we know the rest. So from here, we isolate, okay, instead of s, actually you can write 1 over square root of x squared plus y squared here, because s can be written in terms of x and y. Okay, so we put in the values. So ds dt is 30, x and y are, we put it in 0.8, 0.6 squared and take the square root, and then x is 0.8, dx dt is unknown, y is 0.6, and dy dt is negative 100. If you put everything in, you get dx dt as positive 112.5 kilometer per hour. So we are going to say at the moment in the question, the car speed is 112.5 kilometer per hour towards east. That's why the answer is positive. Let's look at the example 4. Example 4 is about a particle P that's moving. I want you to look at the picture in here. We have a circle here. The point P was at this point at y 0 to 10. This is the point 0 to 10, and it's moving toward on the circle towards right. And consider as P moves on, consider the tangent line that you're going to draw. This tangent line is going to intersect the x-axis, and there's the intersection point Q. Each time the P is coming towards right, this Q is going to move towards left. Yeah. And the question is, okay, let's read. A particle P moves clockwise at a constant rate along a circle of radius 10 meters centered at the origin. So this is the radius of the origin, the radius of the circle. The particle's initial position is 0, 10 on the y-axis, which is here, and its final destination is the point 10, 0. It wants to go to this point here. Okay. Once the particle is in motion, the tangent line at P intersects the x-axis at the point Q, which moves over time. That's right, Q is moving over time. If it takes the particle 30 seconds to travel from start to finish, so it's going to travel from this point to this point in 30 seconds. How fast is the point Q moving along the x-axis when it is 20 meters from the center of the circle? Okay. So at first 20 meter it is saying. So if you are interested in how fast is the point Q moving along the x-axis when it's 20 meter from the center of the circle. So it's 10 meters here, and it's a little bit more, 20 meters here that they're asking. Okay, so we draw the picture as it is on the left. This theta is the angle that is going down, decreasing actually, because it was at the beginning, it was 9 pi over 2, and it's going down and down and down. So as time passes, the theta dt is decreasing. Because of that, it's going to have a negative sign. Let's do some calculations. For example, we know that in 30 seconds it's gonna go through pi over 2 units or radians, but in 1 minute it's gonna go pi radians. So in other words, we can say d theta over dt is negative pi because of that. Okay, because dt is like 1 minute, d theta is how much radians it takes to move in 1 minute is just pi. So we put negative in the front. The reason is theta is decreasing. Okay, let's move to the next page to write down the relationships. Next, yeah, they are asking, so x is the distance at time t from the point Q to the origin. Okay, so we want to find dx dt when x is 20 and d theta dt is negative pi radian per minute. So what is the relationship we can come up with? We have to relate x and theta. So we have this angle theta, we have the right angle triangle, so x cosine theta is equal to 10 is a good relationship between x and theta. Or you can change it to x is equal to 10 secant theta, because secant is 1 over cosine. You can move this cosine to the right, and x is equal to 10 secant theta is a good relationship between x and theta. Then let's take the derivative with respect to time. Dx dt is equal to the derivative of secant theta with respect to time is secant tangent, and then we use the chain rule times d theta dt, and we keep the 10 here. Okay, and d theta dt we found that it's negative pi. We just put it in, so dx dt is equal to negative 10 pi secant theta tangent theta. So we are interested in dx dt when x is equal to 20 meters. Alright, so we have to find what is theta when x is 20. When x is 20, let's write x is 20, cosine theta is 1 over 2. So whenever cosine theta is 1 over 2, secant theta is 2. So we can just write secant theta here. Tangent theta is square root of secant squared minus 1. You know the relationship, right? Tangent squared theta plus 1 is equal to secant squared theta. We use that identity to isolate tangent theta. Tangent theta is square root of secant squared theta minus 1. And then secant theta is 2. Put it in. 4 minus 1, it is 3, square root of 3. So we put tan theta here, secant theta here, and we get that dx dt is equal to negative 10 pi, 2 times square root of 3. So at the end we get negative 20 square root of 3 pi. At the moment in question, the point Q is moving toward the origin at the speed of 20 square root of 3 pi, which is approximately 109 meter per minute, and the sign is negative because it is traveling towards west. Okay, that's the end.